This lecture covers Chapter 22, Stars from Adolescence to Old Age, Chapter 23, The Death of Stars, and Chapter 24, Black Holes and Curved Spacetime. As a reminder of the properties of stars, stars are found in the mass range of 0.08 times the mass of the Sun to 100 times the mass of the Sun. The luminosity ranges are from 0.00001 times the luminosity of the Sun to 1,000,000 times the luminosity of the Sun. The sizes range from 0.01 times the radius of the Sun for white dwarfs to 1,000 times the radius of the Sun for supergiants. The temperature ranges are from about 3,000 Kelvin for M stars to over 40,000 Kelvin for O stars. This pie chart shows the distribution of masses of main sequence stars as determined by surveying the local solar neighborhood. The vast majority are stars the size of the Sun and smaller. Based on observations of stars with well-known luminosity and mass, astronomers found a power law relating mass and luminosity. The data are presented in the figure. Luminosity is proportional to mass raised to the power 3.5. The exponent 3.5 is an average value over a wide range of main sequence star masses. For main sequence stars, the luminosity of a star can be determined from its stellar classification. The mass can be determined from the luminosity. The table shows the luminosities for the spectral types O5 through M5. Recall that the 5 designates a cooler temperature than a 1 on the spectral type. Hydrostatic equilibrium allows us to calculate what's happening in the interior with our understanding of how matter emits light as a function of temperature, how light interacts with matter, and how different gases behave with pressure or temperature. The Sun's nearly constant existence for billions of years is evidence that the Sun must be in balance. We understand this balance as hydrostatic equilibrium. The prefix hydro indicates fluids, such as liquids or gases, and the suffix static indicates that there is a steady balance inside the Sun. The equilibrium inward gravitational force must be balanced by an outward pressure. At each location in the Sun, some physical quantities are equal to one another. When this happens, we say things are in equilibrium. Any gas at any temperature has a pressure. We are accustomed to thinking about the pressure of the atmosphere or the pressure in a bicycle tire. Consider a small parcel of the Sun somewhere in the interior. There's an inward force from gravity on the Sun. There is an outward force or pressure from the nuclear reactions taking place at the center. These two forces must be in equilibrium. If they were not, the Sun would either collapse in on itself or blow itself apart. Knowing the mass and radius of the Sun, we know where the gravitational force is produced. Since the Sun is in equilibrium, this means we know the amount of force necessary to keep the Sun in equilibrium. The only reactions that can produce this necessary force are nuclear reactions. Since we also know the Sun is primarily made of hydrogen, the reactions occurring at the center must be hydrogen fusion. Mathematical models consistent with observation and physical principles provide further information about the Sun's interior. What powers stars? Keep in mind that fossil records go back over 3 billion years. Radio dating dates rocks and meteors to over 4 billion years. The Sun emits a tremendous amount of energy each second. We also know that the Sun has been shining for about 4.6 billion years. These two facts mean that the Sun must have an energy source to replace the energy that is radiating into space. This energy source needs to be sustainable for a very long time. Hermann von Helmholtz showed that if the Sun were powered by coal, it would last only about 5,000 years. In 1854, he said that the Sun's own gravity could supply an appreciable amount of energy. If the Sun were gradually shrinking, if all of its matter were gradually falling toward its center, enough energy could be released to keep it radiating for a fairly long time. He calculated this source could provide the Sun's energy for times of the order of up to 20 million years. But there was a problem. Lord Kelvin calculated the cooling time of Earth based on gravitational contraction. He found an age between 200 million and 400 million years, older than the age of the Sun. In 1898, the Curies discovered radioactivity. In 1903 and 1904, George Darwin, grandson of Charles Darwin, found the age of the Sun was at least 750 million years. In 1920, spectroscopic analysis found the Sun is mainly composed of hydrogen. In 1939, Hans Bethe proposed that the Sun contained in its core hydrogen nuclei moving at very high speeds. Whenever this nucleus undergoes fusion to form a nucleus of a heavier element, such as helium, a large amount of energy is liberated. Ordinary chemical processes, such as burning, that is oxidation, are inadequate energy sources. The Sun's energy comes from the fusion of hydrogen nuclei into helium nuclei. This takes place in the central core of the Sun. The energy released by this process is sufficient to keep the Sun hot for about 10 billion years. Hans Bethe was able to explain the birth of stars. Nuclear fusion occurs when two or more like-charged nuclei are forced together and combined to create a heavier and different nucleus. In the process, a great deal of energy is released. If the temperature of a gas is over 10 million Kelvin, the nuclei are moving fast enough to overcome the repulsive forces. A star becomes a main sequence star when its core temperature exceeds 10 million Kelvin. This figure illustrates the concept of nuclear fusion. The nucleus of an atom consists of two types of particles, protons and neutrons. Protons and neutrons have approximately the same mass. Protons have a positive electrical charge. Neutrons have no electrical charge. About 90% of the atoms in the Sun are hydrogen. In the core, which is hot, the protons move around at high speeds. Temperature is a measure of the average speed of motion. Like charges repel, so electrical forces would push the protons apart if they came close to one another. In order for nuclear fusion to take place, atomic particles must get very close to one another, enough for the strong nuclear force to act. This strong nuclear force is a powerful but short-range force that holds atomic nuclei together. Due to the high temperatures and high densities in the core of the Sun, the protons can get close enough to fuse. When two protons fuse, they create a deuterium nucleus, which is a neutrino plus a neutrino and a positron. A deuterium nucleus is one proton plus one neutron bounded together. A neutrino is a very light particle that does not interact well with other matter. And a positron is an anti-electron. It has the same mass as an electron, but the opposite charge, and when an electron and a positron collide, they annihilate each other and release energy. Just a reminder to pay attention to the vocabulary. Astronomers sometimes refer to proton-proton fusion as hydrogen burning, even though no chemical changes are taking place and no oxygen is consumed. Keeping with that metaphor, the helium that results is sometimes referred to as helium ash. When low-mass stars, such as the Sun, are on the main sequence, fusion takes place in the core. There are two processes that can take hydrogen and convert it to helium. A protostar becomes a star when the internal temperature reaches 10 million Kelvin and proton-proton fusion begins. The fusion reactions taking place in the Sun are primarily proton-proton reactions. However, between 1 and 2% of the Sun's energy is generated by the carbon-nitrogen-oxygen cycle, hereafter referred to as the CNO cycle. Wiseacre and Bethe explain the fusion process that takes place in main sequence stars. The proton-proton chain requires a critical temperature around 10 million Kelvin and dominates in the low-mass stars. The CNO cycle fuses 4 protons to produce 1 helium nucleus, 2 positrons, and 2 electrons. It uses carbon, nitrogen, and oxygen as catalysts to increase the reaction rate. The positrons and electrons annihilate each other almost immediately after they are released, and this produces gamma rays. In stars, the CNO cycle commences around 14 million Kelvin and dominates when the core temperature is about 17 million Kelvin. The star leaves the main sequence when the fuel supply of hydrogen in the core is exhausted. The nuclear reactions in the Sun start with 4 hydrogen nuclei, each in the single proton, and end up with 1 helium nucleus. This is called the proton-proton chain. The total mass of the original 4 protons is 1.007 times greater than the mass of the helium nucleus. In Einstein's theory of relativity, energy and mass are equivalent to one another. The relationship between them is given by the famous equation E equals mc squared. Here E is a quantity of energy, m is an amount of mass, and c is the speed of light. Because c is a very large number and c squared is an extremely large number, a small amount of mass is equivalent to a large amount of energy. The mass of the helium nucleus is smaller than that of the original hydrogen nuclei because binding energy is released during fusion. Binding energy is the amount of energy that must be supplied to pull things apart. It would take energy to pull the 4 particles in the helium nucleus apart against the nuclear force that holds them together. For stars like the Sun, this is the primary method of nuclear fusion. The proton-proton chain can be conceptualized as a 3-step process. Step 1, 2 protons fuse to make a deuterium nucleus and also releases a neutrino and a positron. This step occurs twice for a single proton-proton chain reaction. The deuterium nuclei and proton fuse to make helium-3. Helium-3 is the nucleus of 2 protons and 1 neutron. This also occurs twice for a single proton-proton chain reaction. Step 3, 2 helium-3 nuclei fuse to form a helium-4 nucleus and 2 unbounded protons. Helium-4 is a nucleus of 2 protons and 2 neutrons. The CNO cycle. As in the proton-proton chain reaction, the CNO cycle fuses hydrogen into helium. In the CNO cycle, carbon acts like a catalyst. A catalyst is a substance that increases the rate of reaction without itself undergoing any permanent change. Carbon combines with 4 protons and 2 electrons, producing 1 helium nucleus. Gamma rays and neutrinos. In high-mass stars, the CNO cycle is the dominating fusion reaction taking place. When the hydrogen supply is used up, the star leaves the main sequence, exiting to the right as it cools, gaining size and luminosity. CNO and the PP chain's dominance on the main sequence. The break point comes around 8 solar masses. A star below 8 solar masses cannot attain a central temperature of 14 million Kelvin, so the primary source of power is the PP chain. Above 8 solar masses, the star's core is above 14 million Kelvin, so the CNO cycle dominates. Einstein showed that the mass and energy are equivalent. There is a net loss of mass in the proton-proton fusion reaction, which is accounted for by the energy that is released. This process is often called hydrogen burning, even though it has nothing to do with chemical burning. Nuclear fusion and burning are 2 very different things. All main sequence stars generate energy the same way, by hydrogen burning in their cores. The mass of the Sun is 2 times 10 to the 30 kilograms. The luminosity of the Sun is 3.8 times 10 to the 26 watts. Over the lifetime of the Sun, 0.7% of the hydrogen is converted into energy. But only the central core of the Sun, about 10% of the mass, is being converted. The total energy of the Sun, the total energy that the Sun will produce is 1.2 times 10 to the 44 joules. And the lifetime of the Sun is about 10 billion years. Neutrinos are elementary particles of matter with no electric charge and very little mass. Neutrinos are emitted in vast numbers by the nuclear reactions that fuel the Sun. Since the early 1970s, several experiments have detected neutrinos arriving on Earth from the Sun. Neutrinos are emitted directly from the core of the sun and escape, interacting with virtually nothing. Being able to observe these neutrinos would give us a direct picture of what is happening in the core. Unfortunately, they are no more likely to interact with Earth-based detectors than they are with the sun. The only way to spot them is to have a huge detector volume and to be able to observe relatively rare single interaction events. We worked through a back-of-the-envelope calculation to estimate the life expectancy of the sun at 10 billion years. We can show that the lifetime is proportional to the ratio of luminosity to mass. Because of the mass-luminosity power law, which with algebraic rearrangement, we can write the lifetime of any main sequence star as being equal to the product of the lifetime of the sun and the star's mass in solar masses raised to the power of minus 2.5. From this, the lifetime of main sequence stars is calculated. This brings us to a completely counterintuitive finding. The most massive stars have the shortest lifetimes by several orders of magnitude. Notice that the brighter blue-white O stars survive only about 360,000 years, whereas the sun will have a lifetime of 10 billion years. Smaller, cooler stars have lifetimes on the order of 490 billion years. Stars have an additional classification imposed on them, the population. Historically, two populations of stars were identified, population 1 and population 2 stars. Population 1 stars are in the disk component of the galaxy. They have a wide range of ages from 0 to 10 billion years old. The youngest ones are in the spiral arms. Population 1 stars' orbits are orderly, roughly circular orbits close to the midplane of the galactic disk. Young star clusters made of population 1 stars are called open clusters because the stars are loosely bound together, in contrast to the old concentrated globular clusters. Population 1 stars have a greater abundance of elements heavier than helium than the population 2 stars. The population 1 are said to be metal-rich. The population 2 stars inhabit the halo and bulge of the galaxy. They are old. Ages range from 10 to 13 billion years old. So they have masses less than or equal to 0.8 solar masses. Their orbits are much more randomly oriented than the population 1 orbits and are highly elliptical. The halo stars are metal poor, 0.001 to 0.03 times solar abundance. But the abundance increases inward toward the center. The bulge stars have metal abundance of 1 to 3 times that of the sun. Early in the history of the galaxy, there was probably a lot of star formation and death in the bulge component, so the metal content rose quickly. The star formation rate in the disk has been more steady, so it's slowly catching up to the bulge's metal abundance. Star formation now occurs in just the disk. Eventually, the new disk stars will be born with greater metal abundance than the metal-rich bulge stars. Population 2 stars were added when the Big Bang models were developed. The very first stars formed would have not had any metals at all, since they had not been synthesized yet. This makes it very difficult for the CNO cycle to initiate if there is no carbon in the universe. The population 3 stars start burning with the proton-proton chain, which does not produce enough energy to support the star, so it continues to collapse. It continues to heat up and the triple alpha process begins, which produces carbon, allowing the CNO cycle to start. This requires that the stars to be very big, perhaps greater than 150 solar masses up to 1,000 solar masses, although there is some disagreement on the smallest population 3 stars possible. These very high mass stars would have spent through their entire nuclear fuel quickly, lifetimes between 2 and 3 million years. The population 3 stars from massive supernova events, which can completely destroy the star or become black holes, seeds of the supermassive galactic black holes. These stars are important in a variety of ways, from star formation, creation of black holes, to the evolution of the early universe. The mass of a star determines almost everything about the star's life. Where a star will be on the main sequence, its luminosity, its temperature, its spectral type, its size, the path it will take when it runs out of fuel, and its eventual state when it dies. Stars are broken down into two broad categories: low mass, average like the sun, or high mass. Their life cycles are different depending upon the mass of the star. The distinction occurs around 8 solar masses. Below 8 solar masses, a star is a low mass star. Above 8 solar masses, a star is a high mass star. The low mass stars, less than about 8 solar masses, quietly leave and eventually become white dwarf stars. The high mass stars go out with a bang. They become neutron stars, pulsars, and black holes, as we'll discuss later. Very low mass stars, 30% of the mass of the sun, have lifetimes of hundreds of billions of years before they consume their hydrogen. The sun will burn its hydrogen for about 10 billion years before it runs out. In the core, fusion changes hydrogen to helium. Eventually, the core depletes its supply of hydrogen. Then there is not enough hydrogen to maintain energy generation in the core, and the star loses its outward pressure. It is no longer in hydrostatic equilibrium, and the core starts to collapse. The figure shows the radial cross-section of the fraction of the hydrogen in blue to the helium in purple for 3 sun-like stars. To the left represents the hydrogen to helium ratio of the sun when it formed about 4.3 billion years ago. The center plot is the sun today, with a buildup of helium ash at the core and a depletion of hydrogen in the core. Today, roughly only 35% of the mass of the core is hydrogen, although the outer shell, called the radiative and convective zones, have the same composition as the sun when it was formed. In 5 billion years, there will be no more hydrogen at the center and not enough left in the core for fusion to continue. At that point, the sun will run out of hydrogen and leave the main sequence. The time it takes to use all the star's hydrogen depends on its mass. Now we'll look at what happens when the sun grows old. As the core is depleted, it begins to shrink. When the core shrinks, its gravitational pull gets stronger. Stronger gravity leads to higher pressure, which leads to faster nuclear reactions, which leads to more energy produced. This pushes the outer envelope away, and the star gets larger. The main sequence is the shaded curve with the number 7 indicated on it, the position of a star like the sun. A star does not spend all of its time on the main sequence. It evolves and moves in temperature and luminosity. In summary, a low mass star makes predictable, circuitous journey on the HR diagram as it dies. It becomes a red giant, then an AGB star, then a planetary nebula, and finally a white dwarf. The path, the numbers 7 to 14, shows the evolution of a star like the sun. This table shows the amounts of time the star spends in each step and how big, luminous, massive, and hot it is. When there is only non-burning helium ash remaining in the core collapses and the star evolves off the main sequence. The plasma in the core is completely ionized due to the high temperatures. The electrons are pushed together very tightly. When it is packed as tightly as it can be, it is called electron degenerate matter. It is so dense that a piece of volume of a standard 6-sided die would have more than 1,000 kilograms of mass. The resulting higher pressure and temperatures lead to hydrogen fusing in the shell outside the core. This is the giant phase in which the core has been fully converted to helium. A star in the red giant phase has a helium core where no nuclear fusion occurs, but gravitational contraction does produce energy. The collapse causes the region around the core to heat up to the point where nuclear fusion can occur in a hydrogen layer surrounding the helium core. The outer envelope, the visible surface, expands because of increased energy production below the surface. The outer surface cools because of the increased surface area. Since the star is expanding but cooling, the overall luminosity increases. The hydrogen burning shell generates more energy than the core did. It has access to a much larger volume of the star's mass, and the star increases sharply in luminosity and expands to the size to become a red giant. The star is brighter, produces more energy. Its pressure has increased such that its surface area has become very large, and the surface temperature of the star drops into the K and M spectral type regions. The sun will eventually become a red giant. Astronomers aren't sure how big the sun will grow when it becomes a red giant. It may become as large as the orbit of Venus or even the orbit of the Earth. If it survives, the Earth will become uninhabitable. Although fusion stops in the core, which is now filled with electron-degenerate matter, outside the core, hydrogen burns. Astronomers call this the hydrogen burning shell. As more helium ash piles atop the core, the interesting and counterintuitive behavior of electron-degenerate matter is revealed. The core gets smaller. The more massive electron-degenerate matter is, the smaller it is, which is the opposite of what most matter of everyday experience. Electron-degenerate core behavior triggers a chain of events that dominates the one solar mass star's evolution for the next 50 million years. Degenerate matter produces stronger gravitational forces. The increase in pressure and energy production results in a larger size and a lower surface temperature. The star becomes larger, more luminous, cooler, and redder. It travels to the land of the red giants on the HR diagram. This red giant has a radius of more than 50 solar radii and a luminosity several hundred times the solar luminosity. However, the core is much smaller and denser. With the extensive surface area, the star cools at a faster rate, so the temperature of the star is dropping even though the luminosity increases and the interior is hotter. This is what makes it redder. As the helium core shrinks, its density and temperature increases. When hot and dense enough with the core temperature of 100 million Kelvin, helium fusion begins. Helium fuses to carbon via the triple alpha process. The figure diagrams the triple alpha process. 3 helium nuclei fuse to create a single carbon nucleus plus energy. This figure illustrates the journey of a one solar mass star off the main sequence and along the red giant branch. As the star exhausts the hydrogen in its core, it leaves the main sequence and moves upward and to the right on the HR diagram, cooling the temperature of its vast surface but increasing its luminosity. Since the surface layers regulate the cooling so that it can't become cooler than a red giant type, the rate of increase in luminosity increases as the star progresses. This is similar to the visual analogy of a snowball rolling down a hill. The larger it gets, the faster it rolls. Similarly, the cycle of hydrogen shell burning surrounding its degenerate helium core feeds on itself. The red giant phase ends when the temperatures in the central core rise high enough for the new nuclear reactions to begin. At this stage, the small, dense core of electron-degenerate material reaches the critical temperature for helium fusion. Within seconds of helium ignition, the thermal pressure increases to the point where the helium core literally explodes. This explosion is called the helium flash. The bright star in the center of this image is not the star of the show. At the bottom center is a rather unremarkable smudge of red, which is in fact a rare and valuable object. First discovered by an amateur astronomer, Yukio Sakuri, in 1996, and noted as a nova-like object, Sakuri's discovery turned out to be far more interesting than the supernova he initially supposed it to be. The object is actually a small white dwarf star undergoing a helium flash, one of only a handful of examples of such an event ever witnessed by astronomers. Normally, the white dwarf stage is the last in the life cycle of a low-mass star. In some cases, however, the star reignites in a helium flash and expands to return to a red giant state, ejecting huge amounts of gas and dust in the process, before once again shrinking to become a white dwarf. It is a dramatic and short-lived series of events, and Chury's object has allowed astronomers to a very rare opportunity to study the events in real time. The white dwarf emits sufficient ultraviolet radiation to illuminate the gas as it is expelled, which can be seen in this image as the ring of red material. Helium fusion results in rapid collapse of the star and subsequent heating of the surface. The fusion reaction in the core allows the core to expand. The pressure in the outer layer subsides, allowing them to contract. Once helium fusion begins, the star travels on the next leg of its journey along the horizontal branch. The name horizontal branch refers to the diagrams of older star clusters where there is a sequence of stars sticking out from the red giant branch along a horizontal line, where they have nearly constant luminosity. Helium fuses to carbon in the core, while hydrogen fuses to helium in the surrounding shell. The star progressively becomes smaller and hotter than a red giant. When the helium is used up in the core, hydrogen and helium fusion continues in the concentric surrounding shells. For the Sun, it will not get hot enough for the carbon to fuse, and the plasma in the core is non-degenerate. The star increases in luminosity and cools. These stars are called asymptotic giant branch stars, and for short, AGB stars. As the luminosity temperature radius relation prescribes, the radius also increases, and this time to a much bigger size than a red giant. The AGB star exceeds the size and luminosity of a red giant. The fusion occurring in the outer layers surrounding the core causes the outer atmosphere to expand. As the star expands, some of the material leaves as a stellar wind. This mass loss means the star cannot hold on to the outer layers easily. Eventually, the outer layers are ejected into space. The ejected material creates a planetary nebula. Note that planetary nebulae have nothing to do with planets. The remaining star shrinks and becomes hotter, moving rapidly from right to left across the HR diagram. The star ionizes the gas in the expanding outer layers, causing the planetary nebula that we can observe. Planetary nebulae do not last forever. Eventually, the gas disperses. The first observed planetary nebula had circular appearances, hence the name. But now we observe examples with much more complex structures. The ultraviolet radiation from the white dwarf may ionize the gas in the ejected layers, causing them to glow. After a planetary nebula is formed, there is a remnant star left called a white dwarf. It is the naked core of the star after the outer atmosphere is expelled. A white dwarf is about half the mass of the Sun, with the other half was blown away. It is the size of the Earth with a density of 1 to 2 tons per cubic centimeter. It is composed of carbon and oxygen with little or no hydrogen or helium, which was expelled in the planetary nebula phase. The leftover core of the star remains as a white dwarf, with a mass of 0.6 to 1.4 solar masses, and about the size of the Earth. It is hot, but not very luminous due to its small size. White dwarfs slowly cool because no nuclear fusion is occurring anywhere in the star. They cannot collapse further because the gravitational force is not enough to overcome electron degeneracy. The final demise of a low-mass star is to become a white dwarf. Sirius B is the closest known white dwarf to the Sun at 8.6 light years. When fusion stops, the star becomes a dwarf. Sirius B is a white dwarf companion of the larger and brighter Sirius A. The white dwarf is considered dead, and it will cool gradually over a long time. However, there is a way to bring them back to life. The zombie nature of some white dwarfs will be discussed next. The pulsar PSR J2222-0137 has a low mass companion, 1.05 solar masses. The calculated temperature of the white dwarf is no more than 3,000 Kelvin. Astronomers believe that such a cool collapsed star would be a largely crystallized carbon, not unlike a diamond. This graphic shows the entire evolution of a Sun-like star given a relative sense of how long each stage takes. The figure shows the predictable path of a low-mass star when it runs out of fuel. On the HR diagram, it spends the majority of its life on the main sequence. Eventually, the hydrogen runs out and it evolves off the main sequence, making a circuitous journey first to the region of red giants, then swings wildly to the left, reaching very high temperatures, and suddenly downward to the region of white dwarfs. Such stars never become hot enough for fusion past oxygen to take place. Putting these pieces together, we have the stages of stellar evolution from the time the Sun-like star leaves the main sequence. After the hydrogen in the core is fully depleted, the star leaves the main sequence, first becoming a subgiant, then a red giant. The star does not expand and cool indefinitely. There are internal limiting processes. Buildup in the core of electron degenerate matter leads to a helium flash that lasts only a brief moment. At that moment, it becomes an AGB star moving horizontally back toward the main sequence and fusing both hydrogen and helium. When the helium in the core is depleted, it has a carbon core. This non-degenerate plasma does not support fusion. Instabilities in the helium fusion lead to pulsing that ejects much plasma into the space as a stellar wind. The remaining core is hot, it shrinks and cools. The luminosity declines during this cooling stage and no fusion takes place. Eventually, the stellar wind blows the planetary nebulae away, leaving just a small, hot, but not very luminous white dwarf. Nova means new star. A nova is a star that flares up very suddenly and then returns slowly to its former luminosity. Recall that most stars are in binary systems. Here, two low-mass stars orbit each other about their center of mass. In each pair of low-mass stars, the more massive star evolves first. The more massive star will become a white dwarf before the less massive star. As the larger two solar mass star ages, it expands. It can only expand so much before it begins to lose material. If the stars orbit close enough to each other, the material can flow from the giant star to its companion. In this example, the two solar mass star will lose mass when it is in the AGB phase, and material flows onto the one solar mass star. This occurs because the star expands to the point where the gravitational pull of the other star strips away material. This is called mass transfer, and the system is called a mass transfer binary. During this process, the smaller one solar mass star becomes more massive. Eventually, the two solar mass star becomes a white dwarf. When the second star, the one solar mass star, is a giant, it can dump material back onto the white dwarf. The maximum mass for a white dwarf is 1.38 times the mass of the Sun, known as the Chandrasekhar mass. If material dumped on the white dwarf pushes it over this limit, the white dwarf will explode as a supernova. Recurrent nova can occur only in binary systems. Mass transfer occurs until enough material accumulates on the surface of the white dwarf companion that a brief burst of nuclear fusion occurs. mass transfer and nova events can repeatedly occur between the two stars. Material falls onto the white dwarf from its main sequence companion. When enough material has accreted, fusion can reignite very suddenly, burning off the new material. Material keeps transferring to the white dwarf and the process repeats. There are two different fates. In the first type, the white dwarf receives a critical mass and erupts as a nova. It then becomes a white dwarf, and the system becomes two white dwarfs orbiting their center of mass. In the second type, the white dwarf attains a mass of 1.38 solar masses and erupts into a type 1a supernova. The supernova event can completely disrupt the star and leaves an isolated giant that becomes a lone white dwarf. The violent explosion for a white dwarf companion is called the type 1a supernova. The explosion is briefly as luminous as 10 billion suns. Nothing of the white dwarf is left behind. The other star continues to evolve on its own. Type 1a supernova are recognized by their light curve. All type 1a supernova have the same light curve. They have the similar composition and same mass, and practically the same brightness, which is the same absolute magnitude. They can be used to measure distances to distant galaxies since they are so bright and can be seen across most of the universe. This is an example of a type 1a supernova in the galaxy M101, the Pinwheel Galaxy. As we saw in the first lectures, the high mass stars reach extremely high temperatures, burn very quickly, and are dominated by CNO cycle fusion, whereas the low mass stars are long-lived and dominated by proton-proton chain reactions. When the hydrogen is exhausted, the star leaves the main sequence to the right, where they are cooler and larger. The luminosity does not change greatly at first. The luminosity appears nearly constant. The intermediate range stars of 6 to 10 solar masses, which includes both low mass and high mass stars, however, almost immediately enter a region known as the instability strip, where their luminosity is not constant. Now we will describe the onion skin models of shells of fusion reactions in high mass stars and compare and contrast the post-main sequence evolution of low mass and high mass stars. High mass stars are on the road to disaster since high mass stars go out with a bang. They end in supernova events. As we saw in the first lectures, the high mass stars reach extremely high temperatures, burn very quickly, and are dominated by CNO cycle fusion, whereas the low mass stars are long-lived and dominated by proton-proton chain reactions. When low mass stars deplete the hydrogen in the core collapses, eventually being supported by electron degeneracy. Hydrogen fuses in the surrounding shell during its red giant phase, which ends with a helium flash producing carbon. Similarly, when the high mass stars leave the main sequence, they expand and cool, but that is about all they have in common with the post-main sequence evolution of low mass stars. Basically, everything proceeds differently in high mass stars. As the internal pressure and temperature rise, helium fusion gradually begins in the core, which remains non-degenerate. The temperature continues to rise as this happens, and additional reactions take place, provided those reactions produce rather than consume energy. Before discussing the sequence of fusion processes, let's outline the considerations of the energetics of fusion. In a nuclear reaction, the total relativistic energy is conserved. Mass, however, is not conserved. That means that the energy balance going into the reaction and yielded by the reaction must account for differences in the rest mass of the participating particles. The periodic table is consulted here to find the rest masses of the particles, and the difference is called the missing rest mass. Einstein's mass-energy relation, the famous E equals mc squared formula, is used to compute the nuclear binding energy that was released by the rest mass lost in the reaction. Fusion reactions release energy in the form of kinetic energy, that is, the energy of motion of the product particles, the emission of high-energy photons called gamma rays, the excited energy states of the product nuclei, which are metastable and subsequently is released through nuclear decay, and the energy of excited electron states, which is subsequently released as X-rays when the configuration of its electron shells reaches the ground state. Exothermic reactions release kinetic energy. Endothermic reactions require kinetic energy. Fusion is the combining together of lighter atoms into heavier elements. For all main sequence stars, the temperature and density in their cores are so great that hydrogen atoms combine to make helium atoms and release energy, a process known as thermonuclear fusion. In the fusion process, 4 hydrogen nuclei are converted into 1 helium nucleus plus the release of energy. This energy is what powers the stars for billions of years. When core hydrogen fusion ceases, a main sequence star becomes a giant. When hydrogen fusion ceases in the core, the star will collapse inward. This causes the layer just outside the core to become so hot and dense that hydrogen fusion will begin in the outer layer. The energy produced by hydrogen fusion in this layer just outside the core causes the rest of the star to expand into the giant phase. Helium fusion begins at the core of a giant. When the exterior layers expand, the helium core continues to contract and eventually becomes hot enough, 100 million Kelvin, for helium to begin to fuse into carbon and oxygen. 3 helium go to 1 carbon plus energy, or carbon plus helium go into oxygen plus energy. What happens after the core helium fusion stops? The shell and the core equilibrium game continues. Depending on the mass of the star, heavier elements are produced: carbon, oxygen, neon, silicon, and the heaviest element being iron. What about elements heavier than iron? Heavy elements such as uranium have unstable nuclei, which decay to lower energy states through a process called fission. In fission, a nucleus spontaneously splits into 2 lighter nuclei, releasing a tremendous amount of energy. The discovery of nuclear fission made the development of an atomic bomb a theoretical possibility. Nuclear power plants get their energy by fission. Exothermic reactions give up energy as they occur. In contrast, an endothermic reaction takes energy to proceed. Fission is an exothermic reaction. It gives up lots of energy as shown by the atomic bomb. Fusion reactions are high energetic reactions in which 2 lighter atomic nuclei combine to form a heavier nucleus. Fusion, discovered by German chemists Otto Hahn and Fritz Strassmann in 1938, and its theoretical explanation by Lisa Meitner and Otto Frisch, can be exothermic or endothermic. Whether a reaction is exothermic or endothermic depends upon the mass of the nuclei. Fusion reaction from hydrogen up to silicon are exothermic. To fuse iron and heavier elements is endothermic reaction, since energy must be supplied. Here's a periodic table of elements showing the processes that created them. As we learned in Chapter 1, the Big Bang event produced the hydrogen and helium of the universe. In physical cosmology, Big Bang nucleosynthesis, also known as primordial nucleosynthesis, produced lithium and beryllium in the early universe. All the elements that are heavier than lithium were created much later. Processes involving the fusion of elements lighter than iron are possible in evolving stars. Processes involving the fusion of iron and heavier elements, because they require input energy, are only possible in exploding stars, in supernovae. The very heaviest elements are man-made in atom smashers. Massive stars follow the CNO cycle from fusing hydrogen to helium. As the star evolves off the main sequence, it burns helium to produce carbon. In a low-mass star, after the helium flash produces carbon in what is known as the triple alpha process and occurs rather quickly. In contrast, in a high-mass star, helium fusion is a much slower process. In high-mass stars, when the core depleted of hydrogen begins fusing helium, the outer shell continues to fuse hydrogen, since throughout their interior, massive stars have hot temperatures. Likewise, when the helium supply is depleted inside the core and carbon fuse dominates there, the shell surrounding the core continues helium fusion, and the surrounding that, there is a shell where hydrogen fuses. Further evolution causes the core temperature to rise as the star contracts, and carbon fusion produces sodium, neon, and magnesium. The neon and oxygen start to fuse. Thus, the more massive the star, the heavier the elements it can produce. Our current model is that of a high-mass star evolves, layers of concentric shells, each with unique fusion processes, forms heavier elements toward the center. This structure is called the onion skin model. Extreme high-mass stars have strong stellar winds, such as Eta Carinae in the figure. The mass loss rates of high-mass stars are orders of magnitudes higher than low-mass stars. The winds reach several thousand kilometers per second. Eta Carinae is an example of an unstable star. It is too massive for a stable main sequence star to form. In the process, it undergoes outbursts of mass loss. The core fusion rate of increasingly heavier elements at each successive stage requires less time to exhaust their fuel supply. The heavier the fusion process, the more neutrinos produced. These neutrinos are unimpeded and carry away energy, and this cools the star. During these fusion stages, the star zigzags more or less horizontally on a path to the right on the HR diagram. For all high-mass stars, the path leads on a tremendous, violent explosion called a supernova. The figure shows supernova 1987A that exploded in a small companion galaxy of the Milky Way called the Large Magellanic Cloud. On the left is a picture taken before the supernova. On the right is a picture taken near the supernova's peak brightness. The core collapse process and the fact that unlike a type 1a supernova, which destroys a white dwarf, the supernova that is part of the death of a high-mass star leaves behind a very dense core. Now we will discuss the end life of a high-mass star and a core collapse and a supernova event, and understand that there are mass-based end stages of the neutron stars and black holes. All high-mass stars end with a supernova. A supernova is a one-time event. Once it happens, there is little or nothing left of the progenitor star. There are several types of supernovae. Type 1a, which is a carbon detonation supernova, white dwarfs that have accumulated too much mass from binary companions. Type 2a, which is the death of a high-mass star, and types 1b and 1c are less common deaths of a high-mass star that involve mass loss. Recall that a high-mass star can fuse elements heavier than helium. Each day is progressively shorter. Carbon burning lasts for 1,000 years. Silicon burning only lasts for a few days. Fusion of iron or more massive elements requires an external energy source. Once a star has an iron core, it cannot generate more energy by fusion. Fusion stops and the core collapses. A type 2 supernova is the rapid collapse and violent explosion of a high-mass star when core fusion processes stop. This happens when the core is mostly iron. Neutrino byproducts exit the star carrying away energy. This is called neutrino cooling. The decrease in core temperature results in instability. The cooling mechanism at work are neutrino cooling and photodisintegration. The core can no longer hold up the outer layers, which now collapse inward. A visual analogy is like trying to inflate a balloon that has a hole in it. The basic steps of core collapse are follows. As the core collapses, its temperature rises. Photodisintegration and neutrino cooling reduce core temperature and pressure, accelerating the collapse. The core collapses due to the force of gravity until it reaches nuclear densities. Core collapse stops and bounces back, driving a shock wave through the star. The shock wave takes a mere few hours to rip through the star. The figure illustrates the basic stages of core collapse that result in a Type II supernova. Starting from the top and working downward, the electron degeneracy pressure cannot stop the collapse of an iron ash core in a high-mass star. As the core collapses, the temperatures are so high that the photons disintegrate iron through a process called photodisintegration. The core becomes tremendously dense. Reverse beta processes combine protons and electrons to form neutrons. The photodisintegration, electron absorption by protons, and the cooling by neutrinos reduce the pressure in the core, which in turn accelerates the collapse. The density becomes so high that the nuclei repel each other. The over-compressed core suddenly and violently expands, driving its outer layer through the star. This is called core bounce. The shock wave created by the core bounce is enhanced by the hot bubble of neutrinos in the core and travels outward, heating the outer layers to extreme temperatures that are violently blown off the star. This extreme dense core is left behind. These collapsed remains will become either a neutron star or a black hole. Based on light curve analysis, while the progenitors of Type II supernova return both their hydrogen and helium envelopes prior to explosions, Type 1b supernova lose their hydrogen envelope prior to explosion, and Type 1c supernovae appear to lose both the hydrogen and helium envelopes, resulting in an almost featureless spectrum at early times. The figure shows the brightness reached by supernova 1987A. In a Type II supernova, outer layers blow off in a tremendous explosion, and the light emitted is equivalent to 1 billion suns. The figure shows how the supernova impacts its surroundings. Its shock wave heats the interstellar medium. Most atoms heavier than iron are created by the explosion. These elements are then ejected into the interstellar medium by powerful winds. During the supernova, a tremendous amount of energy is released. Some of the energy is used to fuse elements heavier than iron. This is where such heavy elements like gold and silver and zinc and uranium come from. The material gets ejected into space as a result of the supernova and becomes part of the interstellar medium. New stars and planets form from this interstellar medium. Since the interstellar medium has been polluted by heavy elements from supernova, the planets that form from the interstellar medium contain some of those heavy elements. The collapsed core is also left behind by a Type II supernova explosion. If the mass of the core is less than 2 or 3 solar masses, it becomes a neutron star. If more than 2 or 3 solar masses remains, not even neutron degeneracy pressure can hold the object up, and it collapses into a black hole. We know from earlier that the Big Bang created light elements like hydrogen, helium, and lithium. The Sun is a low-mass star and capable of fusing or creating elements that are heavier than carbon. But when we look at the Sun spectrum, we see evidence of elements that have higher atomic numbers than iron. What does that tell us? That tells us that the Sun is not a first-generation star. It is made from the remnants of supernova that happened long ago. Okay, now we will look at the remnants of the core collapse and resulting supernova, the end stages of neutron stars and black holes. After a Type 1a supernova, death of a white dwarf, little or nothing remains of the original star. After a Type 2 supernova, death of a high-mass star, part of the core may survive. If the core is less than about 3 solar masses, it will form a neutron star. The collapse is halted when neutrons are packed as tightly together as rules of quantum mechanics allow. The core is now neutron degenerate, the mass between 1.4 and 3 solar masses, but with a diameter of only 10 kilometers. Compare a ball that is 10 kilometers in diameter to Manhattan. The ball has a 1 to 3 solar mass. That makes it 1 billion times denser than a white dwarf and 1,000 trillion times denser than water. The first pulsar was discovered in 1967. It emitted extraordinarily regular pulses. Nothing like it had ever been seen before. After some initial confusion, it was nicknamed LGM for Little Green Men. It was realized that it was a neutron star spinning very rapidly. Why do neutron stars spin so rapidly? Recall the conservation of angular momentum and the collapse of nebula to form stars. Now the star is collapsing, and it must conserve angular momentum. From that blinking point of light, astronomers learned that there are other important properties of neutron stars besides mass and size. The rate of rotation is important. As the parent star collapses, the neutron core spins very rapidly, conserving angular momentum. Typical periods are fractions of a second. The strength of the magnetic field is important. Again, as a result of the collapse, the neutron star's magnetic field becomes enormously strong. As a highly magnetized neutron star rotates rapidly, light is emitted, much like the beam of a rotating lighthouse. From our perspective, as these beams sweep past us, the star appears to pulse on and off, and this is why they are called pulsars. Pulsars are rapidly rotating neutron stars. The Crab Nebula is the result of a supernova observed by Chinese astronomers in 1054 AD. Surprisingly, there are no clear references to the supernova from Europe. The Crab Nebula pulsar is evidence that our models of the evolution of high-mass stars are correct. The nebula, as we've seen today, consists of remnants of the Farmer star that collapsed in 1054 AD. The spinning pulsar at the heart of the Crab Nebula sends off a wind of electrons and positrons moving at close to the speed of light. A pulsar's strong magnetic field directs its emitted radiation in line with the magnetic poles. These are called jets. If the rotation axis is not the same as the magnetic axis, which is common for all solar system objects, the two beams will sweep out circular paths. If Earth lies in one of those paths, we will see the star blinking on and off as we do in the Crab pulsar. This composite image of the Crab Nebula shows the X-ray in blue and the optical in red images superimposed. The size of the X-ray image is smaller because of the higher energy X-rays emitted. Electrons radiate away their energy more quickly than the lower energy optically emitting electrons as they move. The Crab Nebula pulsar provided X-rays for an observation that determined the thickness of Saturn's moon, Titan. Very rarely, Saturn transits the Crab Nebula. Its transit in 2003 was the first since 1296. Another will not occur until 2267. Observers used the Chandra X-ray Observatory to observe Saturn's moon Titan as it crossed the nebula, and found that Titan's X-ray shadow was larger than its solid surface, due to absorption of X-rays in its atmosphere. These observations show that the thickness of Titan's atmosphere is 880 kilometers. The transit of Saturn itself could not be observed because Chandra was passing through the Van Allen belt at the time. Pulsars radiate their energy away quite rapidly. The radiation weakens and stops in a few tens of millions of years, making the neutron star virtually undetectable. Pulsars also will not be visible on Earth if their jets are not pointing our way. The pulses in luminosity can be seen in gamma ray light as well. An isolated neutron star has been observed by the Hubble telescope. It is moving rapidly, has a surface temperature of 700,000 Kelvin, and is about 1 million years old. If the neutron star is in a close binary with a red giant, large amount of X-rays can be emitted. As the red giant expands, it fills its Roche lobe. Material can flow from the red giant to the neutron star, where it is accelerated and emits X-rays. Bursts of X-rays have been observed near the center of our galaxy. A typical one appears at right as image in the X-ray spectrum. These X-ray bursts are thought to have originated on neutron stars that have binary partners. The process is very similar to a nova, but much more energy is emitted due to the extremely strong gravitational field of a neutron star. Most pulsars have periods between 0.03 and 0.3 seconds, but a new class of pulsar was discovered in the early 1980s, the millisecond pulsar. Millisecond pulsars are thought to be spun up from matter falling in from a companion. This globular cluster has been found to have 108 separate X-ray sources, about half of which are thought to be millisecond pulsars. Now we will look at how black holes can be formed and related concepts including event horizons, spaghettification, the Schwarzschild radius, and Hawking radiation. A type II supernova explosion leaves behind a collapsed core that can become a neutron star, if the mass of the core is less than 2 or 3 solar masses. However, if the core is more than 2 or 3 solar masses, not even neutron degeneracy pressure can hold the object up, and it collapses into a black hole. Mass transfer in a neutron X-ray binary system can also form a black hole. When Einstein published his theory of general relativity, the complicated field equations enticed physicists to find solutions. In 1915, Karl Schwarzschild provided the first exact solution to the Einstein field equations of general relativity. It was for a limited case of a single spherical non-rotating mass. His solution led to the derivation of the Schwarzschild radius, which is the size of the event horizon of a non-rotating black hole. Here, r is the radius of the spherical object. If r is less than 2 times m, no problem. But if r is equal to 2 times m, the denominator is equal to 0. M is the product of the universal gravitational constant, the mass of the non-rotating sphere, and c is the speed of light in a vacuum. The value of r that makes this denominator in that term equal to 0 is known as the Schwarzschild radius. When you divide a finite number by 0, the answer is undefined, but in mathematics it is given the name singularity. The physical significance of this singularity and whether this singularity could ever occur in nature was debated for many decades. Finally, in the second half of the 20th century, there was general acceptance of the possibility of a black hole. Einstein's field equations, together with Karl Schwarzschild's solution, predicted the existence of black holes before astronomers had the capability to detect them. A black hole is a singularity in space-time, where the strong gravitational pull has distorted spacetime to an extreme amount. Newton's law tells us the gravitational force increases with increasing mass and decreasing radius. We calculated the escape velocity of objects from the surface of planets. If the object is massive enough and small enough, the escape velocity will exceed the speed of light, so that not even light can escape. At a singularity, the escape velocity is infinite. This is why these objects are called black holes. Light cannot escape from them. Light that is emitted near the black hole will be shifted in wavelength on its way out. There is a distance near the black hole such that light never gets out, and that is called the event horizon. The radius at which the escape speed from the black hole equals the speed of light is called the Schwarzschild radius. Earth's Schwarzschild radius is about a centimeter. The sun is about 3 kilometers. Once a star has collapsed into a black hole, the Schwarzschild radius takes on another meaning. It is the event horizon. No events inside the event horizon can influence an outside observer. A consequence is that nothing within the event horizon, not even light, can escape the black hole. Black holes are singularities in spacetime. The warping of spacetime causes extreme tidal forces and gravitational redshift. The event horizon is a sphere with a radius known as the Schwarzschild radius, where the escape velocity equals the speed of light. Black holes have a gravity so strong that even light cannot escape. The tidal forces cause objects falling into the black hole to stretch greatly. This is called spaghettification. Just like neutron stars, black holes can exist in X-ray binary systems with other stars. The strong gravitational pull can result in powerful X-rays from the accretion disk behind it. Stephen Hawking was a well-known cosmologist and theoretical physicist. He collaborated with Roger Penrose on gravitational singularity theorems in the framework of general relativity and the theoretical prediction that black holes emit radiation due to quantum effects near the event horizon. Hawking was the first to set forth a theory of cosmology explained by a union of the general theory of relativity and quantum mechanics. Hawking also has written popular science books explaining his theories in terms of a general audience can understand. Recommended reading for this course is a book titled A Brief History of Time, in which he explains cosmology, including the Big Bang, black holes, and light cones. A quantum mechanical effect called Hawking radiation should result in a loss of energy and therefore also decrease in the size and mass of a black hole. If a particle and an antiparticle were created at the event horizon, one of those objects might not escape the black hole. The energy of the black hole would have gone into the initial creation of those particles. The black hole would lose energy when it only recovers half of the energy used to create them. This is known as black hole evaporation. This amount of Hawking radiation would not be very much at an instant, so we would find it difficult to use it as a signature for detecting black holes. Star N6946-BH1 before and after it vanished out of sight by imploding to form a black hole. The typical view is that a star can form a black hole only after it goes supernova, said Ohio State astronomer, professor, and study researcher Christopher Kochnick in the press release. If a star can fall short of a supernova and still make a black hole, that would help explain why we don't see supernova for most massive stars. Galactic black holes like M87 and the Milky Way black hole are not formed by the collapse of a star. They're likely formed as a galaxy itself was forming by the collapse of dense material at the center of the galaxy. Now we want to define the instability strip and describe the property of the stars in the instability strip. Any star that shows a variation in brightness is classified as a variable star. Variable stars do not have constancy of luminosity. Main sequence stars generally have a constancy in their luminosity, except when some extrinsic process causes apparent changes. Such systems include eclipsing binaries, eclipsing planets, and rotating stars with huge surface variations. The figure shows a screenshot of the University of Nebraska's eclipsing binary simulator and the periodic changes in apparent magnitude that would be observed from the Earth. Systems like these that have extrinsic causes of luminosity changes will vary both on and off the main sequence. The instability strip on the HR diagram is a narrow region above the main sequence which contains many types of variable stars. These variable stars exhibit periodic or pulsating changes in luminosity or irregular fluctuations, much different than the eclipsing variable stars like Algol. Intrinsic variables include pulsations of temperature and size, flares and mass eruptions, and cataclysmic explosions such as novae and supernovae. Over 30,000 variable stars are cataloged and classified as either intrinsic or extrinsic, depending on underlying causes. The two most famous types of variable stars are Cepheid variables and R.R. Lyrae variables. Both these types of stars obey a period luminosity relationship, meaning that their period of variability corresponds to a unique absolute luminosity. Opacity is the measure of the impenetrability to electromagnetic or other kinds of radiation, especially visible light, in radiative transfer. Singly ionized helium, helium that has lost 2 electrons, and stars in the instability strip pulsate due to the opacity of doubly ionized helium. When the star contracts, density and temperature increases, and more singly ionized helium becomes doubly ionized. This in turn increases the star's opacity, so that less light is radiated away from the star. With that cooling mechanism quenched, the internal temperature of the star rises. Rising temperature causes the star to expand, which cools the star and reduces the fraction of doubly ionized helium. The opacity decreases, allowing more light to radiate out of the star. This cools the surface temperature, and the cycle repeats as the cooling star again contracts. Giant stars pulsate because their atmosphere traps radiated energy. This heats outer layers, making them expand. Expanded gas cools, pressure drops, and gravity pulls the layer back in. The cycle will start all over again. Plots of the magnitude variation of 2 Cepheid variables. The variation is regular and predictable. Pulsating variables have predictable light curves. Light curve analysis reveals a periodicity of the luminosity fluctuations. Cepheids, R.R. Lyrae stars, R.V. Tauri stars, and long period stars are all types of pulsating variables. Henrietta Swan Leavitt was an American astronomer who revolutionized astronomy by discovering the period luminosity relationship of Cepheid variables. After graduating from Radcliffe College, she traveled to America and in Europe, during which time she lost her hearing. She had family financial support, and although deaf, she volunteered as a research assistant at Harvard College Observatory under the astronomer Edward Pickering, who had initiated a research program on the measurement of stellar magnitudes. 7 years later, in 1902, Pickering hired Leavitt to the observatory's permanent staff at 30 cents per hour. Leavitt worked until her death and received little recognition for her contribution during her lifetime. In the early 1900s, women were not allowed to operate telescopes, and Pickering did not want women to work on theoretical studies. Instead, the ladies measured and cataloged the brightness of stars as they appeared in the observatory's photographic plate collection. Sometimes called Pickering's harem, these ladies were regarded as human computers. Leavitt was eventually given the task to study variable stars. Henrietta Leavitt studied the variable stars and noticed patterns in the light curves. Some had distinct periodicities. She measured the period. The period and magnitude variation of a few Cepheid stars are discussed in an online article titled The Top 12 Naked Eye Variable Stars, written by John Iles, published in Sky and Telescope in March of 2010. Leavitt measured 1,777 variable stars and images in the Magellanic Clouds. These are small, irregular galaxies in the local group of the Milky Way galaxy and are seen in the southern hemisphere. In 1908, she published her results in the Annals of the Astronomical Observatory of Harvard College, noting a pattern. Brighter stars appear to have longer periods. In 1912, she concluded that the Cepheid variables with greater intrinsic luminosity did have longer periods, and that the relationship was quite close and predictable. Leavitt used the simplifying assumptions that all the Cepheids within each Magellanic Cloud were at approximately the same distance from Earth, so that their luminosity could be deduced from their apparent brightness. She wrote on her discovery, a straight line can readily be drawn among each of the two series of points corresponding to maxima and minima, thus showing that there is a simple relation between the brightness of the variables and their periods. Since luminosity can be inferred from period and absolute brightness could be measured, the period-luminosity relationship allowed astronomers to determine the distance to Cepheids and the entities that were embedded in other galaxies. Pickering did not allow Leavitt to follow up on her groundbreaking research. However, her contribution revolutionized astronomy. The period-luminosity relationships of Cepheids helped map the shape of the Milky Way, and Harlow Shapley's view of the galaxy changed, as Cepheids showed the Sun is not at the center of the galaxy. Erwin Hubble, using Cepheids, found the distance to other galaxies was very large, and these objects were outside of the Milky Way. This resolved the great debate of whether galaxies were clouds in the Milky Way, which at the time was considered to be an entire universe, or, as they are now known, separate galaxies in their own right at great distances. Hubble was also able to show that the Milky Way was not the center of the universe, and, using the period-luminosity relationship and spectral shifts, defined Hubble's law that the universe is expanding. Henrietta Leavitt changed our understanding of the size and shape of the universe. Her efforts would have won her the Nobel Prize, but she died of cancer in 1921 at the age of 53. She was considered for nomination, but the Nobel Prize is not awarded posthumously. The asteroid 5383 Leavitt and the crater Leavitt on the Moon are named after her to honor deaf men and women who have worked as astronomers. When she looked at the 25 of the brightest Cepheids, they took longer periods of time to complete each pulse, to reach their maximum brightness, dim, and return to maximum again. While all the stars vary by approximately the same amount in terms of visual magnitude, the ones with the highest average brightness took months to cycle from bright to dim to bright again. As the average brightness of the observed stars decreased, so did the period of the star's variability. The dimmer a star was, the faster its brightness varied, down to a minimum of just over a single day. In fact, she found that there was a well-defined correlation between how bright a Cepheid appeared on average and the period of time it takes to pulse. Let's put these pieces together to estimate the distance to sky and telescope examples. Delta Cephei's magnitude ranges from 3.5 to 4.4 in the cycle of 5.37 days. From the luminosity period relationship, it is found to have an absolute magnitude of minus 3.47. We can then use the distance modulus to find the distance as 247 parsecs. Eta Aquilae has a magnitude range of 3.5 to 4.4 and a period of 7.18 days. from the luminosity-period relationship, it is found to have an absolute magnitude of minus 3.7. The distance modulus yields a distance of 275 parsecs. These values are crude estimates, and catalog values are slightly different. This Hubble shows RS Puppis, a Cepheid variable. RS Puppis varies in brightness by almost a factor of 5 every 40 or so days. RS Puppis is unusual. This variable star is shrouded by thick dark clouds of dust, enabling a phenomenon known as light echoes to be shown with stunning clarity. In a December 2015 article of Universe Today titled "Watch a Star Blast Out Waves of Light," Jason Major writes that the images are assembled from observations made over the course of 5 weeks in 2010 and shows RS Puppis pulsing with light outbursts that are then reflected off the structure of its surrounding nebula. What look like expanding waves of gas are really light echoes, radiation striking the densest rings of reflective dust located at farther and farther distances from the star. The flow of neutral or charged gas ejected from a star's upper atmosphere is referred to as a stellar wind. These variable high-mass stars have strong stellar winds. The structure of them is revealed by the light they emit. In summary, pulsating variables have a predictable light curve. Light curve analysis reveals a periodicity of the luminosity fluctuations. Cepheids, R Lyrae stars, RV Tauri stars, and long period stars are all types of pulsating variables. These pulsating variable stars are extremely important for determining distances. Cepheid variables are high-mass stars on the path to becoming supergiants. Their pulsation periods are from 1 to 100 days. R Lyrae stars are low-mass stars on the horizontal branch. They have periods of days. By analyzing light curves, astronomers can determine that the period and hence luminosity of the star. The distance is determined using the distance modulus. Because they are bright, Cepheids are particularly useful for finding distances to galaxies. This HR diagram shows the location and names of all the distinct variable type stars observed. The numbers of these stars is actually quite small compared to the total number of stars on the main sequence. When stars are born, they develop from large clouds of molecular gas. This means that they form in groups or clusters, since the molecular clouds are composed of hundreds of solar masses of material. After the remnant gas is heated and blown away, the stars collect together by gravity. During the exchange of energy between the stars, some of the stars reach escape velocity from the protocluster and become runaway stars. The rest become gravitationally bound, meaning they will exist as a collection of orbiting stars forever. When a cluster is young, the brightest members are O, B, and A stars. Young clusters in our galaxy are called open clusters. Due to their loose appearance, they usually contain between 100 and 1,000 stars. One example is shown as the Jewel Box cluster. The following series of HR diagrams shows how stars of the same age but different masses appear as the cluster as a whole ages. After 10 million years, the most massive stars have already left the main sequence, whereas many of the least massive have not even reached it yet. After 100 million years, a distinct main sequence turnoff begins to develop. This shows the highest mass stars that are still on the main sequence. After 1 billion years, the main sequence turnoff is much clearer. After 10 billion years, a number of features are evident. The red giant, subgiant, asymptotic giant, and horizontal branches are all clearly populated. White dwarfs indicate that solar mass stars are in their last phases also appear. This double cluster, H and Chi Persei, must be quite young. Its HR diagram is that of a newborn cluster. Its age cannot be more than about 10 million years. The Hyades cluster shown here is also rather young. Its main sequence turnoff indicates its age of about 600 million years. This globular cluster, M80, is about 10 to 12 billion years old, much older than the previous examples. Since all the stars in the cluster formed at the same time, they are all at the same age. A very young cluster will have an HR diagram with a cluster of T-Tauri stars evolving towards the main sequence. As time passes, the most massive stars at the top of the main sequence evolve into red giants. Therefore, the older the cluster, the fewer stars to be found at the top of the main sequence. And an obvious grouping of red giants will be seen at the top right of the HR diagram. Observations of star clusters are performing photometry on as many individual stars that can be measured in a cluster. Each star is plotted by its color and magnitude on the HR diagram. Shown below is one of the diagram for the globular cluster M13. Note that the main sequence only exists for low mass G, K, and M stars. All stars bluer than the turn-off point have exhausted their hydrogen fuel and evolved into red giants millions and billions of years ago. Also visible is a clear red giant branch and a post-red giant region, the horizontal branch. The animation is a detailed computer-simulated HR diagram. The horizontal axis is the log of the temperature. The y-axis is the luminosity of the star, and the main sequence is the line through the middle of the figure. Notice the stars evolving off the main sequence labeled by their masses in solar masses. The high mass ones first. To the right is a diagram of the interiors of the three stars, masses 2.6, 1, and 0.7 solar masses. The cutaways show what happens inside the star as they evolve. Notice the enlarging envelopes as the star become red giants. In this lecture, we looked at stars on the main sequence and how stars move off the main sequence as they evolve. Along the way, we discovered giant stars, white dwarf, supergiants, supernovae, neutron stars, pulsars, black holes, and variable stars.